Another thing I want to remind you is if you're ever using the addition rule with the classical approach, and you're going to get a fraction for one probability and a fraction for the other using the classical approach, and then you're going to add those two fractions, it's best to not reduce your fractions until after you've added the two fractions. The reason why is according to the classical approach, you always start off with the same denominator for all probabilities, which is n, the number of simple event components. So if you don't reduce your fractions till after you add in general, you'll always end up with fractions that have the same denominator. That way they'll be easier to add, and then you can always reduce the sum of those two fractions into lowest terms after you've added them. So I'll leave both of my individual fractions here using the classical approach as unreduced fractions, just in case, just to ensure that I get the same denominators. So the probability of getting an ace is 4 over 52, and then plus the probability that you'll draw a king. Well, there's also 4 kings in a deck of cards. So for the probability of drawing a king, you would get what? Also, you'd get 4 over 52. 4 kings divided by 52 cards. So the answer is 4 over 52 plus 4 over 52. Okay. And I guess that's kind of hard to see. There you go. And now, since I have a common denominator, of course I could have put 1 over 13 in both cases here, as it turns out, and that would have been okay. But just to be on the safe side, I left these unreduced. Now I can add them just by adding the tops and keeping the common denominator, and I get 4 plus 4 divided by 52, or 8 over 52. And 8 over 52, if I divide 4 out of the top and bottom, that reduces to 2 over 13 as a simplified fraction. So I could either leave my answer for part 3b as 2 over 13, or if I use my calculator to write this as a decimal and round to 4 significant figures, you'll get 2 divided by 13 is 0.1538. So I could write my answer as either 2 over 13 or 0.1538, which is a decimal approximation for 2 over 13 that's rounded to 4 decimal places. 4 significant figures. So here 4 significant figures was 4 decimal places because the first non-zero decimal place was the first decimal place. But anyway, so either 2 over 13 or 0.1538. And once again, this is the minimum amount of work you need to show on the test for this part. All right, so now we move on to 3C. For problem 3C on the test, it says, what's the probability you'll draw either an ace or a spade? So once again, it's an either-or statement. So we have another compound probability here, the probability that either the event E occurs or the event F, but now we're saying what's the probability of drawing either an ace or a spade? So here E is draw an ace, and F is the event that you draw a spade. So we have a compound probability, just like we did in part B, but now we're saying what's the probability you draw an ace or draw a spade. So before we decide which formula to use between formulas 1C and 1D, we have to decide whether E and F are mutually exclusive events or they're not mutually exclusive. Is it possible to draw both an ace and a spade at the same time in one single draw? Or another way to say this is, if you looked at all the simple event components that led to an ace and all the simple event components that lead to a spade, are there any common simple events between the event E and the event F? Are there any cards that are both aces and spades? And the answer is there is one card that is a simple event component for both E and F, namely the ace of spades. So there is a common simple event component. As long as there's at least one common simple event component between two events, the two events are not mutually exclusive. So that means these are not mutually exclusive events. And what that means is there must be an event called E and F. And if you remember from the notes, the event E and F is made up of all simple event components common to both E and F. And in this case, the simple event components common to both E and F, there's only one simple event component for E and F, and that's namely the ace of spades. So, since these are not mutually exclusive events, and the event E and F does contain at least one simple event, we have to use Formula 1D, which is the general addition rule for compound probabilities, which says that when E and F are not mutually exclusive, the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. So according to Formula 1D, we have to use a slightly more general version of the addition rule. We already know the probability of E is 4 over 52. And so this ends up equaling 4 over 52, which is the probability of getting an ace, plus what's the probability of getting a spade? Well, how many simple event components lead to a spade? If you look at a deck of cards, 13 of the cards are spades, 13 of the cards are hearts, 13 are diamonds, and 13 are clubs. So there's 13 simple event components that lead to a spade. Namely the ace of spades, 2 of spades, 3 of spades, 4 of spades, all the way up to king of spades. So the probability of getting a spade is 13 over 52 by the classical approach. And then we say minus, what's the probability that you get both a spade and a ace at the same time? Well, there's one simple event component, namely the ace of spades, that makes up the event E and F. So once again, if we use the classical approach for the probability of E and F, it would be equal to 1 divided by 52. 1 for the one simple event component making up E and F divided by the 52 simple events for the procedure. So probability of E and F is just 1 over 52. So the full probability is 4 over 52 plus 13 over 52 minus 1 over 52. Make sure all that's in there. And that equals, since they all have the same denominator, I just add up the numerators. 4 plus 13 is 17. 17 minus 1 is 16. So the answer is 16 over 52 as an unreduced fraction. Then I notice that this is not fully simplified. So if I want to write my answer as a fraction, I need to divide 4 out of the top and bottom, which leads to 4 over 13, which is a reduced fraction. Or if I want to write that as a decimal rounded to 4 significant figures, it comes to approximately 0.3077. So you can either write your answer for 3C as 4 over 13 or as 0.3077. And like I said, all these calculations are in the solution key for test 3, and this would be the minimal amount of work. You don't have to put what E and F are, and you don't have to put this part, but you do have to show the rule, the addition rule from Formula 1D, and you do have to show this basic calculation here, and either write this or this as your answer. All right, so let's move to problem 3D. So for problem 3D, the question is, suppose you draw 4 cards in a row from the deck, sufficiently shuffled deck, but you replace each card you draw and reshuffle before you draw the next card. So remember in class we called this drawing cards with replacement. And the reason why we say draw cards with replacement here is so that you end up with independent trials. Because drawing 4 cards in a row has natural repetition. You can naturally break that procedure of drawing 4 cards in a row with replacement into 4 individual trials, one draw at a time. Where the first draw is the first trial, the second draw is the second trial, and so you end up with 4 total trials, one for each draw. And the only way, it says, what's the probability of drawing 4 aces in a row? Well, the only way you can get 4 aces in a row is if you set this up event by event so that the first event, the result of the first draw has to be an ace. And then what? The second event for the second draw also has to be an ace. So if you write this in the notation for Formula 1E, which is the multiplication rule for n independent trials, you would get the probability that you would draw an ace on the first draw, and then you would draw an ace on the second draw, and then you would have to draw an ace on the third draw, and then finally you'd have to get an ace on the fourth draw. This is the only way to break the event of getting all 4 cards to be aces into a sequence of events, trial by trial, as if each individual draw led to an ace. So if you set this up, and of course since we're drawing cards with replacement, the probability that any one draw leads to an ace is not affected by what happened on any of the other draws. Since you're always sticking the card back in the deck and reshuffling, you're always drawing from a fresh deck of shuffled cards, so the probability of getting an ace on any one draw is not affected by whether or not you got an ace on or not on any other draw. So these are independent events. Now, if you didn't replace the cards between each draw, you would not get independent events, and you would have to use a different version of the multiplication rule. But here, we do have independent events, so by Formula 1E, this would just be the probability of getting an ace on the first draw times the probability of getting an ace on the second draw times the probability of getting an ace on the third times the probability of getting an ace on the fourth. And the probability of getting an ace on the first draw would be what? 4 over 52. Now, when you're using the multiplication rule, you don't have to write your fractions unreduced. You're not adding fractions here, you're multiplying. You're going to be multiplying fractions, so there's no need for a common denominator when you're using the multiplication rule. So it's best for each of these individual probabilities to be reduced as far as you can reduce them into lowest terms before you multiply. So if you do that, the probability of getting an ace on the first draw, we found out from part A of this problem, is 1 over 13. It's 4 over 52, which reduces to 1 over 13. And of course, the probability of getting an ace on the second draw is also 1 over 13. And the probability of getting an ace on the third is also 1 over 13. And the probability of getting an ace on the fourth draw is 1 over... So the answer is 1 over 13 times 1 over 13 times 1 over 13 times 1 over 13. And if you wrote that as an exponent, it would be 1 over 13 raised to the 4th power. That all get on there? Okay, 1 over 13 to the 4th power. And if you want to use your calculator now, all you have to do is do 1 divided by 13, hit the equal sign, and then hit your exponent key, and then hit 4. So that would be 1 over 13 raised to the 4th power. And on your calculator, if you do that, you should come up with the decimal rounded to 4 significant figures to be 0.00003501. So the decimal for this probability, rounded to 4 significant figures, is 0.00003501. Once again, all these calculations are on the solution key to test 3. Just make sure you can see that. And if you look at your solution key to test 3, you'll see all these calculations there. Alright, so now we move on to problem, I believe that was the last part of 3, so now we move on to problem 4.